Welcome everyone to my talk about my PhD project, bringing the algorithms to the data. Secure distributed medical analytics using the personal health train. The personal health train started with a manifesto from the Dutch Tech Center for Life Sciences. In order to advance healthcare and biomedical science through a shared infrastructure, the data should be kept under local control by each site independently, and the huge amount of data which is gathered at each site should be machine readability at the core in order to advance data analysis and medical decision-making. Within the GoFair initiative, a personal health train implementation network started across Europe. Within this implementation network, a German subchapter started, where the DI Future and the Smith Consortia from the Medical Informatics Initiative in order to set a standards, guidelines, and specifications for a common core infrastructure and reference different implementations. Currently, the German personal health train is supporting 4 different projects. Within Polar and Leuko Expert showcases about rare diseases, it is really important to combine data from different data sources in order to have a bigger amount of data and to obtain knowledge. The standard approach in multi-center studies is usually to send the data to a central analysis site. After the data is sent away, the hospitals lose control over the data, but obtaining results on an aggregated database is really trivial, and the results can be obtained from the central analysis. Within a decentralized setup, the data stays at each hospital, which is in our case called stations, and the algorithm is wrapped within a train and traveling around station to station in order to build iteratively and update the model. So within the one train, we are including several components, allowing a most flexible extension of our architecture. We are using Docker technologies, including the operating system, a train library containing the logic, the FHIR access to the data sources, and the endpoint specification of the algorithms. Within master images, we are including all software dependencies and packages of the algorithms. Currently, our master images are supporting the programming language Python and R. The master images are updated and maintained by administrators, guaranteeing there is no malicious code going inside. The algorithm and the query are user specified and approved by the station administrators before execution. These have to stay static during the whole execution. The results and the models are created during execution. Those are dynamically updating and are encrypted at rest. Due to the fact of the nature on which kind of data we are operating on, privacy and security is really important to us. Stations can detect manipulation. The access to the data is within only the train library allowed, and the manual execution by administrators is providing a higher guarantee that nothing malicious is ongoing. The results, which are sent away or distributed across different hospitals, are encrypted at rest using envelope encryption. Currently, we are supporting the homomorphic encryption Palia crypto system for adding and multiplying sensitive data across sites. Our researchers can obtain aggregated or final results without revealing sensitive data to different stations. Methods such as k-anonymity, differential privacy, or other secure multi-party computation frameworks are as extensions possible. In order to send an analysis to different sites, we have several service components. Our main goal is to have a robust and well-maintained architecture. We are using several open source components and are adding those with self-implemented components. Our user interface is developed with Vue.js. We are using Message Broker for communication between components. A train builder and a train router and an offline tool are self-developed tools in order to make results available. The container registry is based on Habe, and our secret storage is based on Vault. The train images already mentioned are based on Docker. A station user interface is allowing execution, and we are supporting different identity and access management systems in order to connect each site locally. The user interface is for specification and submission of trains. Later, I will show you a short demo video. The train builder is automating the Docker building process and building valid trains, including the whole key management. The train router is moving the trains between the different repositories. And the offline tool is used locally for the key management, the signing of hashes of the uploaded analysis, and the result decryption. I will also show this within a short demo. The train execution is in total in this figure illustrated over 3 different slides. A user here on the left side can log into the user interface with his associated station. Each user has to be associated at least to one hospital in order to log into the user interface. After requesting analysis and the manual approval of the station administrators, the user can upload his code. The uploading process is including a signing of the algorithms he's submitting and the signing of the hashes with the offline tool. After the validation and the approval of the station administrators, the train is being built. Therefore, a task is sent to the message broker, which is communicating the queue to the train builder to build the train. The train builder is now posting the route to the secret storage and receiving the public keys of each participant. After a successful creation, the train is pushed to the incoming repository in our container image registry. This event is communicated to the message broker. The message broker is now publishing the event to the train router. The train router now receives the route from the secret storage and is moving the train according to its route. In this example, we are executing the train at 3 different stations iteratively. So the train is being moved from the incoming repository to the station 1 repository. Only the station itself and the train router have access to these components or these repositories. From the station 1 repository, the station 1 or hospital 1 is pulling the train. A manual execution is guaranteeing a secure file storage access. The results are obtained and pushed back in an encrypted way to the station 1 repository. At station 2 and in station 3, the same process is happening. After the train router has no stations left in the execution, he's moving the train to the outgoing repository. The results service is pulling the encrypted results and providing the user in the user interface to download these. With the offline tool, the user can decrypt the results and obtain those. Next, you will see a video with the analysis, the submission process of the analysis code. After a successful login, you can see right now the different stations which are included. The user can send a proposal asking to do an analysis. In this case, we're doing the analysis over 3 different sites. The train is being as an analysis train submitted, and we are selecting the NF core example. We have to manually select the stations we want to train on, select the master image and a fire query. Now we can upload our code. Now we need to specify the programming language and the entry point of the train. Now the hash is generated and signed with the offline tool. This digital signature is pasted to the UI and the train can be built. Now the train is building. After the execution at each of the sites, the user can download the results. The encrypted results are downloaded and can be opened with the offline tool. Within the offline tool, the user needs to specify the train configuration, his private key, and select the directory to decrypt the results. Now, the two result files can be decrypted and can be opened within the current Explorer or Finder. In order to show that our architecture is working, I have provided two different showcases. The first showcase is about ISIC image classification, where we want to train a deep neural network to classify 8 different types of skin cancer. Doing such, we are using the 25,000 provided images from the ISIC 2019 challenge. And we're using the code of champions in order to compare a central trained model with a decentral analysis. The execution time of the train was in total around 37 hours, and the result size was 654 megabytes. The total decryption and encryption of the models at each site locally took around 5.5 minutes, which is not a huge overhead compared to the total execution time. For this example, we split the data evenly across all different sites. The central approach has an accuracy about 0.68 and the sensitivity about 0.62 with 60 epochs. We're using the same training and testing splits for the 5-fold cross-validation as provided by the champions of the challenge. For comparison, now in the decentral analysis, we only trained 20 epochs at each station. As you can see here, the results are compared to the central analysis quite good. But what you actually can also see is the problem about crucial forgetting, which means when you train or update a model or deep neural network iteratively across different data sites, a model may lose information about previously learned features. Also, the order of the execution, if you go to station 2, 1, or 3 first, decides the quality of the model. But later I will explain how we can solve such. The second showcase is about HLA-Typing. The task of the train is to execute the NF-core HLA-Typing pipeline with 216 next-generation sequencing samples over 3 sites. The task is to securely count the total number of HLA type B35 or 1 occurrences, which are related or assumed to be related with a fast progression of HIV-related disease AIDS, and plot the total or the absolute most frequent 15 HLA types over all sites. The execution time of the train again was over almost 45 hours, and the result size is quite small. The encrypted results, which can be downloaded in the user interface, look like these. After the decryption, you obtain the plot and the homomorphic encrypted number. Within this plot, you have the different HLA types, the most frequent alleles of the different HLA counts from 3 different stations and the distribution. But in order to decrypt the homomorphic encrypted number, you need to use the offline tool. Within the offline tool, you can copy the encrypted, homomorphically encrypted number and decrypt it with a separate private key, which reveals the result of 24 patients having the HLA type B3501. Our outlook for the future is to deploy our current architecture at hospitals right now. After deployment of our architecture, we are working on a federated learning system which is overcoming the problem of our crucial forgetting. In a federated setup, an aggregator is being updated simultaneously from all sites in the same. In a federated learning setup, we have an aggregator which is receiving the updates from each site in parallel and obtaining the final results in order to obtain a final model. This overcomes the problem of crucial forgetting. Having such architecture also allows for secure multi-party computation and privacy-preserving AOC computation on an exact way without revealing information about each site locally. Finally, I want to thank all to my colleagues from different universities and my colleagues from Tübingen for supporting the project. Additional information about our implementation and our status you can find on the personalhealthtrain.de, and our code base you can find on gitlab.com. Thank you very much for your attention, and now I'm open for questions.